Hey, what's up, guys? This is Chung here. So today's daily challenge, right? Number 295, find medium from data stream. Okay. So this one is a very classic problem. Basically, we're having like a stream of data, right? And we simply need to provide find the medium at any moment, right? For example, if the data stream is like this, if we have 2, 3, 4. So if we want to get a medium, obviously it's 3, right? Because that's a medium, the medium value, right? So if it's an even case, right? So if it's odd case, if it's an even case, then the medium will be this 2 divided by 2, right? So that's it, right? So I mean the some standard constraints here. Right. So this one actually, it's a very classic one. We usually, at least for me, I usually use two priority queue or two heap to solve this problem, right? Because, we want to make like both the add, actually we want to make the add uh, or the find, right, to be at least log n, right, so that it can pass this test case. So there are like other like solutions, but for me, I always prefer two heaps, right? Where the first one is the first one is the maximum queue, the maximum heap, or the second one is the minimum, the mini heap, right? So I think most of you already know this concept. Basically, we use the so let's say we have basically we're trying to maintain, right? Maintain the two potential medium, right? Basically, if we have two parts, right? 2, 3, 4, 5, 6, 7, 8, and 9, right? So basically, this is the two values we're looking for, right? So which means that at any moment, we're trying to use a maximum queue, right? A max queue to 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 maintain the biggest value, right, for the first half, and we're gonna use the minimum queue to, to give us the minimum value of the second half, right? So in that case, right, we can when we uh, try to find the medium, we can simply easily find these two values from the maximum queue, the first one, and the minimum queue for the first one, the first element, right? So once we have this max queue and the minimum queue to maintain the biggest value for the first half and the minimum value for the second half, the only thing we need to consider is how can we maintain, right? How can we maintain, make sure this max queue and the minimum queue, they are kind of balanced, right? So when I say balanced, it means that the difference cannot be greater than 1, right? It's because we have two cases, right? So we have, if we have 2, 3, and 5, 2, 2, 3, 4, right? So in this case, it's the first two, first this thing will be in the first half, and this one will be the second half, right? And so let's say we have a max queue and minimum queue, right? So whenever we have a new numbers coming in, so how should we like manipulate this two priority queue so that the it still maintains the character the property that we're looking for, right? So let's say we have, so the next one is 5, right? So the next one is 5. So whenever a new number comes in, we always add to the maximum queue. Okay. So the reason being is that we're using this kind of max queue as a buffer to hold the new numbers, and then we're going to try to move any number that's to the second part, because when a new number comes in, we don't know if this number belongs to the first half or belongs to the second half, right? So that's why we always add it to the first half regardless, right? So in this case, it's 5, right? So we have 2, 3, and 5 in this one. And every time when we add a new numbers to the to the first one, right? And then we will basically will pop. So after doing a heap push into this one, we have the biggest number, right, so far, and then we're gonna push this we're gonna move the biggest number of the second part into the biggest number of the first part into the second part, which means in this case we're gonna move this 5 into the second part, which is gonna be a 4 and 5 in this case, right? Then that's how we maintain this one. And because let's say for example, right, so because we are inserting 5 here, what if we inserting 1 instead of 5, right? So in this case we're gonna have 1, right? 1. So after this one, once we push the biggest one out of 4, now this time we're gonna move 3 into the second part, which is this one, right? That's what we'll get, right? Right. And then how about at the beginning, right? So at the beginning, so this is the first step. And the second step, once this is done, we also want to check if the first half has less value, has less element than the second half. If that's the case, we also want to move the one element from second half to the first half. So the reason being is that we basically we're making sure the first half always has the same or more element than the second half. That's why whenever we have we're trying to find a medium, right? And if it's even, if it's odd case, we simply just use this max the first half 0 to get the value. Otherwise, we're gonna use both the value from both values, right? And yeah, so that's basically that's the 2 steps, right? So so the first step is that when we always insert, we always we always push into this first half, which is the max queue, the maximum queue, right? And once that is done, right, we're gonna move the biggest one from the first half into the second half, right? That's the way we're making sure all the numbers are still in order, right? And after that, the second step is that we want to check if the first one has less value than the second one, right? So this is the case of, for example, if it's the first value, right? So when the first number comes in, right? So both the max q and minimum q, they are empty, right? Basically, if the first one is 2, so basically 2 will be pushed into the max q, and 2 will be moved into the second half, right? So this is the first half, and this is the second half, right? Now the first half doesn't have anything of the second half, right? And then basically we have to move this 2 back to 1, this 2 back to the first half, so that we will so that the first half will always be either have the same as the second half or have has more than the second half, right? And yeah, in terms of this implementation, right? So we have the self.max max q, right? And the second of the minimum q, right? So in Python, there's only a minimum q. That's why to have a max q, we have to store the negative value, right? So the first step 1 is that always push to first half, right? Which is max q, right? Heap push self.max, right? And then we're gonna do a minimum negative version of it, right? second half, right? And then move the biggest, right? From first half to second half. Okay. So heap push self.minimum q heap pop self.max, right? Because when you pop this one out, that's the maximum, right? But we also need to revert the sign here, right? And then we check if, then we balance the two heaps, right? If the length of the first half is smaller, right, than the length of the second half, then we're gonna also push one from the second half to the first one, to the first half. Okay, right. So that's how we maintain it. I think this one, this one will only happen. Yeah, no, it did. Sorry, though, this one will happen multiple times. If we have like 1 and 5, right? So in this case, right, we have that's the first half and second half. So whenever we have 3 here, right? So we have 3 here. So basically, so we have 1, 3 here, right? And then we'll push 3 to the second half, right? And then this 3 is gone. Now we have 3 and 5 in this one, right? And then once this is done, right? Basically, we're going to move 3 back to here, right? So the reason being is because we want to do this thing is because it seems like an unnecessary movement here. The reason being is because let's say we have uh, let's say the first one is 3, right? And then uh, we're adding 1 here, right? So we have 1 and 3 here, right? So in this case, instead of 1, actually we should push 3 to 5, right? So pushing 3 to 5 here, right? So we have 1, and then we have 3 and 5, right? Now we're so what I'm trying to say is that so now this one we're pushing it back again, right? Yeah, so sorry, so this one is not a good example either because this one we are seems like we're also moving the 3 to second half and then move it back, which seems unnecessary. Yeah, I think this is a bad example. Sorry. Let me try. Yeah, I think this is a good example. So I was trying to show you guys why this is necessary. So let's say we have a 7, right? Okay, if we have 7, right? So we have 3 and 7, right? On the left side. Now 7 will be pushed into 5, right? Now we have 3, and then we have 5 and 7, right? But now, as you guys can see, right? So the medium is 5. So which means that when this happens, right? Instead of 7, 5 will be pushed back to the first half. Now we have 3, 5, and 7, right? That's why we need these 2 steps. Basically, we always push to the first half, and then we balance. We balance we move the biggest one of the first half to the second half, and then when this thing happens, we're gonna move one more from from second half, right? Which is this case, because we always want to get the smallest from second half and move it back to the first half whenever the two heap is not balanced, are not balanced, right? And yeah, so that's it, right? And then so for the final medium, it's pretty straightforward, right? We simply just need to check two case, right? So if if the length of the first half it does not equal the length of the second half, right? Since we are guaranteed that the first half will always be greater or equal than the second half, so this one is the first half is greater than the second half, right? Then we simply return the basically the biggest value of the first half, which is our medium, right? It's going to be the self dot max q dot 0, right? Otherwise, if they're the same, then we have to get two values, right? Which is and we have to do a divided by 2 for those two values. So it's going to be a self dot minimum q, right? Which is the smallest value from second half, and then plus the biggest value from the first half, right? Since the first half is the negative values, we do a minus, right? And then we divide it by 2. So that's it, right? If I run the code, I think this should pass. Q. Okay. Right. So this one works, right? Because the time complexity, as you guys can see, this one the heap is log n, right? And this one is O of 1. So we have at the most this n thing n times, so it's going to be n log n, right? Yeah, so that's it, right? And yeah, so there are like some follow-ups for this problem, right? So the first one is that if all the integers from stream are in the range of 0 to 100, how can we optimize our solution, right? Because for this one, the range of the number is pretty big. What if it's only a 0 to 100? So this one, whenever we have like smaller range of the numbers, it's always a hint for us to use bucket sorting, right? I think most of you know what bucket sorting is. So for this one, it means that we can just use like a size of 100, a list, which will store the count for each of the number from 0 to 100, right? And then we can and then every time when we have like add here, right? Add here, we simply just increase, right? We increase that value. We increase that count for that value, and when we need to find the median, right? We simply just loop through that array, right? With a count, because we know the total counts, and that's when we can just simply loop through that, find the median. Let's see if we can implement that. Let me see that. So for this one, self count, right? Let me see if I can implement that even with this kind of range. So this one is going to be so we have 2 times 10 to the power of 5, right? Can I do something like this? Okay, so if we have this count, right? And then here, right? So let me try to comment out these things here. We simply do a count, gonna be a number plus 10 to the power of 5, because we could have negative values, right? That's why I need to do some offset, right? It's going to be a +1. Okay. I'm not. Let me do a +5 to make sure we have enough space, right? That's the count, right? So, and here, total numbers, right? Total count is going to be 0. So here, every time we simply just do a self dot, okay, of this. I guess I shouldn't I guess this will not work because here, in order for this to work, once we have the count here, basically we need to have a for loop here, right? For loop for this I in range of what? 2 times, right? 10 to the power of 9, right? Of 5, right? And then basically we're simply just accumulating the numbers, right? Until this one reaches half of the total, right? And then we can use that to check if this is a single number is within this current bucket, or we have to move to the next bucket. Also consider the next bucket, right? But as you guys can see, this one, since this one will be of n, right? Times this n is going to be a n square, right? With this kind of big enough numbers, this one will TLE. But I'm just trying to show you guys, um, if it were for this very small range, we can use something like this, right? Bucket sortings. And so that's it. And second one, what if the 99% of integers are integer? How would you optimize a solution? So to this one, I guess we can still keep this bucket, but since we have a 1% values outside of this range, then probably we need to have like another hash map, right, or dictionary to store that the other 1% numbers count, right? And then we can just merge those two together and do some similar stuff to find the medium. Yeah, I think that's pretty much it is, right? Cool. Yeah, I think that's what I want to talk about for this problem. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.